Hi guys, this is Davit. If you hear my voice, that means I'm on my way to my little conference, and I apologize for not being present for the in-person lectures. But thanks to this technology, I'll be able to at least get you guys some of the concepts and important equations and help you study the book. So let's roll with it. As I said, we're trying to go over this hydrogen atom chapter of the book. So I'll be covering the three important concepts, basically, the hydrogen atom wave functions, the spin, and atomic orbitals. So we have a separate lecture dedicated to it. So those of you that were present on today's lecture, right, I sort of set out the foundation. Talked about this note, but I noticed that a lot of you guys are out of town, so why don't I go over this this stuff? It will be good to keep it in a video format. Okay, so I'm gonna use my iPad, and this will allow me to draw on some of the equations. So maybe this is a good technology. So I'm gonna switch to my iPad Notability app, and this is the same content as on the website, so everything is the same. It's just I'm gonna be able to draw things. All right, so we're gonna talk about the solution of the hydrogen atom problem, the predictions that come out when you solve the Schrödinger equation, right? The quantum numbers that you get, eigenfunctions, eigenvalues, and that sorts of things. So we're going to see what kind of predictions the quantum mechanics makes. Okay, so the problem is the hydrogen atom, and to be more specific, we don't care so much about the nucleus, the proton in the hydrogen atom, but more about the electron. Okay, so the proton is going to be fixed. Basically, there's a little ball here, and we mostly care about studying the wave function for the electron that moves within this sort of the fixed field of the nucleus. Okay, and this problem is going to lead us to a lot of interesting results, some consequences of the spherical symmetry of the hydrogen atom. We're gonna pay particular attention, and then we're going to discover the atomic orbitals. Okay, so first of all, the term here is hydrogen-like atoms. Okay, so why not just a hydrogen atom? Because well, you can have a helium plus or lithium 2 plus, and these guys have one electron. Okay, so it turns out that if you only have one electron, you can solve the Schrödinger equation exactly, right? And this is maybe the last problem that we'll look at it, right, in this class, because all the other problems with more than one electron, they do not allow exact solutions, so we have to resort to some kind of numerical tricks. Okay, gonna resort to approximations, and this is one of the reasons why we treasure the hydrogen atom problem. Okay, so it's going to give us that little piece that is going to be the building block that is going to be used to study bonding in multi-electron molecules, and also study multi-electron atoms. It's the fundamental building block. It's the hydrogen atom. Okay, so as we said, we don't care about the proton. It's a two-body problem. Proton is going to be fixed. You're gonna see the reduced mass in some of the parts of the textbook, but generally the mass difference between proton and electron is so huge that reduced mass is approximately mass of the electron, so you can use them interchangeably. So why don't we just stick to one of these, let's say the mass of the electron. But you should know that if you have a two-body problem, it's the reduced mass. All right, so what's the recipe that we've used in quantum mechanics so far, right? The recipe is to write down the Hamiltonian, the classical Hamiltonian, and then replace everything with operators. Okay, so first we look at the kinetic energy. Kinetic energy looks exactly the same as what we've seen in particle in a box, in particular particle in a 3D box, right? So if there was no other potentials, hydrogen atom wouldn't be so different from the particle in a box. Okay, but in this case we do have a fundamental difference, right? We don't have any sort of boundaries, right? And instead we have the attractive interaction of a proton that pulls the electron and keeps it bound, okay, doesn't let the electron fly away and go anywhere, right? And this is the reason, right? We don't need any boundary conditions, because these potential energy or potential, as we often refer, is what keeps the electron bound, and this is what is going to give us quantization of energy values. Okay. All right. So with these two pieces that together comprise the Hamiltonian, we're ready to study the consequences of solution of the Schrödinger equation. And here we're looking at it: kinetic energy and potential energy operators. And you see that we have the wave function expressed in spherical coordinate system. Why spherical coordinate system? Because of the natural spherical symmetry of the atoms, right? So you can think of the hydrogen atom as the heavy nucleus, and then electron that's sort of somewhere out there described by some wave function. Okay, so this is the problem, right? And spherical coordinates are natural choice, and we're gonna stick with it as when we move to multi-electron atoms and molecules. So spherical coordinates are here to stay, and we're going to study some of the consequences of that. Here is the Laplacian operator expressed in spherical coordinate systems. We've looked at this guy in the rigid rotor problem, right? We see that there are three differential terms: one that depends only on r, another one that depends on theta, and another one that depends on phi. Okay, and it's not worth remembering, but it's worth knowing that differential operators look different in different coordinate systems. If you have a Cartesian, it's going to look one way. If you have a spherical, it's going to look different. If you have a cylindrical, it's going to look something else. So, and we can always look this up in Wikipedia and books, and no memorization is needed here. All right, so the spherical part we've already solved, so we don't need to repeat that part here. So just a reminder, right, that the spherical part is proportional to the angular momentum, right? That was the rigid rotor problem. Here you see that we absorbed the parts that belong to the angular momentum operator inside the L hat square. Okay, but then we have still some work to do, because we have the radial part, right? The radial part, we didn't have this problem in a rigid rotor, because rigid rotor, the R was constant, so we just threw away that part. All right, so there is something new to be learned. So this is how the Schrödinger equation looks once we absorb the spherical coordinates inside the angular momentum, right? We see the part that contains the R, and then these parts that are inside the angular momentum. Okay, so one of the reasons to use spherical coordinate systems, or the main reason to use it, is that it captures the symmetry of the problem and allows separation of variables, right? So we're able to nicely and cleanly separate all these variables, r, theta, and phi. And if you remember, the spherical harmonics separate these two, right? The phi part had something like IMF, and the theta part had some polynomials of cosines. So all the three variables separate, and this is the only way to solve differential equations. Okay, so if we used Cartesian coordinate system, this would not be possible. Okay, so this is great. We're able to separate the variables, we're able to divide and conquer the problem, and get the eigenvalues. All right, so the R part is the radial wave function, and the Y is something we've already seen, the spherical harmonics. Gonna give us some beautiful shapes. The spherical harmonics, we've already seen their eigenvalues. This is the eigenvalues for angular momentum, right? As you would expect, they share the same eigenvalues with the hydrogen atom, because it can, the spherical harmonic function is the same, exactly the same. Okay, so we're just going to focus on the radial part, and plugging in the eigenvalues into the Schrödinger equation. We're down to one variable problem that only depends on the variable r, which is the distance of the electron from the nucleus, right? So the nucleus and the little electron that could be somewhere with different probabilities described by a wave function, and it can have different distances. Maybe r here, r prime here, r prime prime there. Okay, so this is a problem we're trying to solve. Now let's try to gain some intuition here, right? Because we're seeing some terms that we can clearly recognize their effect on the wave function, the behavior of the electron. So we see that there is this potential energy form that contains the attractive term, right? There's a negative sign here. Pay attention, that negative sign has a stabilizing effect. It tries to bring the electron to the nucleus as close as possible. But then we have another term that acts oppositely, okay? So in some sense, we can see where the stability can emerge, right? So you have the potential that tries to pull in the electron with 1 minus r dependence. And then we also have the repulsion that comes from the kinetic energy operator. And it has a 1 over r square, right, dependence, and it's trying to push the electron away. Okay, so this shows that we're going to have some kind of a happy average distance where the electron is most likely to be found. Okay, so see that there's two kinds of contributions here. And as we've seen in a particle in a box example, right, the kinetic energy tends to explode the closer you bring the electron, or the more determined you make its position. That's your uncertainty relation, if you haven't forgotten yet, right? So sigma x, sigma p must be at least h bar half. So basically, electron doesn't want to be confined. The more confined the electron, the higher the momentum variance, the higher the kinetic energy. Okay, so we already know this effect, and we already know that electron wants to stay in some kind of a happy kind of distance away from the nucleus. All right, so potential energy is unable to completely take over. And we also see that potential energy here depends on L. Okay, so if L is not 0, right, this term would be activated, and the greater the L, the greater the effect of this force, right, that tries to push the electron away. But when L is 0, thankfully, right, there is this other last term that is going to not let the electron collide with the nucleus. It's going to push it away. Okay, so even if L is equal 0, your kinetic energy is going to make sure the electron doesn't jump on the nucleus and explode the atom. Okay, so your stability is maintained by the balance of kinetic and potential energy. So that's the intuition we're learning. Okay, that's great. And now, after we went over the radial part, we're ready to look at the full solution of the hydrogen atom. And that's something we've seen in chapter 1 when we solved the Bohr model. And unsurprisingly, since the Bohr model gave us the exact energy values, we end up with the same expression of the energy, which is here. Okay, so and the same quantum number n. So the difference is that the Bohr model got here with some crazy mix of classical mechanics and some ad hoc restrictions or conditions that Bohr had to throw at the problem just to get the right answer. Okay, and as you know, if you try to apply the same Bohr recipe to other atoms, these methods of mixing classical mechanics with ad hoc rules just doesn't work at all. Okay, so it's just a happy coincidence because of the nice symmetry of the hydrogen atom that Bohr model worked. But quantum mechanics gives you this expression from first principles. Okay, you write down the Schrödinger equation, you solve it, and you end up with these eigenvalues. Okay, with no assumptions made. Okay, so this is the beauty of quantum mechanics. It gives you a set of recipes, you apply, and you get the exact result. Okay, so the eigenvalues were familiar, quantum number were familiar, 1, 2, 3, it's called the principal quantum number. The radial part of the wave function is new to us, and this is yet another a common mathematical function that is that is well known in the literature, in the literature of mathematical physics, because these kinds of problems have appeared not just in quantum mechanics, but also in other areas. So there are famous mathematicians that have solved this, and these functions bear their name. And this L function is known as Laguerre polynomial, and there's a table, we're going to look at it. And notice that, besides the polynomial, there is this term, the exponential term, that is going to make sure that our wave function decays to 0. So this is important, right? And then, everything is cast in terms of this quantity that's called the Bohr radius. Is going to make the expressions look more clean, okay? And just a notation to make the to make expressions simpler to look at. Okay, so in this kind of in terms of this Bohr radius, we're going to express distance in terms of this dimensionless distance rho. Okay, so, totally unremarkable thing, but it's going to make the expressions look cleaner. And here are the radial wave functions for the hydrogen atom. You can see that the exponential factor is always there, always there, always there. It's going to make sure the wave function decays to 0. If you remember, one of the postulates dictates that wave function must be normalizable, must be finite. Okay, so it's good. The solutions make sense. And you also notice that the polynomials, the Laguerre polynomials, going to introduce nodes into these wave functions. Right, so you go to higher and higher quantum numbers, you're going to get more and more nodes. For instance, here, this guy is going to have nodes where rho is equal to 2, and this guy is going to have 2 roots, rho 1, rho 2, etc. Right, so you're going to keep on adding more and more nodes, and they're going to increase by 1. Okay, so it's a similar picture that we've seen in other quantum problems. Okay, so we're going to explain this notation here, this combination of N and L. We're going to have a shorthand notation where you use the letter S for L0, letter P for L equal 1, letter D for L equal 2. This is a notation that we chemists and chemical engineers, biochemists, are familiar with. Okay, so what we usually did when we solved quantum mechanics problems, we try to connect it with spectroscopy, right? So we connected the harmonic oscillator with vibrational spectroscopy, rigid rotor with rotational spectroscopy, and this problem is connected to electronic spectroscopy because we're talking about energy levels of the electron inside the atom, right? So these different spectroscopies, they use different technology, they use different wavelength, like typical wavelength fall into the UV region for electronic spectroscopy. For the vibrational, it's IR. For for the rotational, it's the microwave. Okay, so nothing new here. You divide energy by hc, go to the spectroscopic units of 1 over lambda, centimeter minus 1. These expressions we've already seen. These factor in front of the parenthesis is the Rydberg constant expressed in centimeter minus 1. So if you want to compute the frequency of the photon when you go from the ground state to some excited state, you can just plug in the values, and here and here and here, and you're gonna get that wavelength. And you can also calculate the ionization energy from any state by putting in the infinity. All right, so these parts we've seen before, but this is the expressions that we arrived by solving Schrödinger equation. Now the big deal in this lecture, right, is to study these new quantum numbers that we haven't seen in Bohr model, right? So we've only looked at n because energy only depends on n. Okay, and this is an aspect that we want to stop and think. Okay, so energy only depends on quantum number n. However, the wave function that depended on theta, phi, and r, right, is expected, right, to depend on all these 3 quantum numbers, and it depends on these 3 quantum numbers, right? We looked at the radial and spherical harmonics. So why wave function depends on 3 variables and 3 quantum numbers, but energy only depends on 1? The answer is the special symmetry of the hydrogen atom, where the only thing that matters is the distance from the nucleus, right? So it's spherically symmetric, so the angles don't make a difference. Only thing that matters is the distance. Okay, that explains why the energy ends up depending only on quantum number n. Okay, and this situation has a word that describes, right? And the word is energetic degeneracy, meaning that regardless of what values the other quantum numbers take, you end up with the same energy. In other words, different wave functions that are characterized with different L and ML values, let's say two wave functions that have different L and ML values, but they share the same value n, they're going to correspond to the same energy En. And we say that we have energetic degeneracy. All right, so notice some of the interesting features with these quantum numbers. N runs from 1 to 3 all the way to infinity, right? And 1 corresponds to the ground state. You have 0-point energy. You cannot make the electron static, so it's always going to move, not to violate the uncertainty principle. Notice that L, however, can take the value 0. It's totally okay. It's totally fine. And these are the s orbitals that we'll shortly see. And L is bounded by n. Okay, so if n is equal 4, L can go all the way up to 3. Okay, so L is going to be 0, 1, 2, and 3. It cannot be equal to 4, okay, because that's a consequence of the solution of the eigenfunction eigenvalue problem, where you end up with these polynomials which turn to 0 if L it matches n. Okay, so mathematically we end up with these results. Okay, so the only wave functions that we get is when L does not exceed n. And same way we have a restriction on m, which we explained the physical meaning of it. So m corresponds to the eigenvalues of the projection of angular momentum operator, so projection cannot exceed the length of the angular momentum, so m is bound to be no greater than L. Okay, so notice these limits, they're important, they have physical significance, right? And finally, there will be a new quantum number which we'll introduce in subsequent lectures, and this will be known as spin quantum number. For now, we just list it here. It's a funny looking quantum number, we'll discuss later. For now, we're just going to ignore it. All right, so we're going to illuminate this meaning of these L quantum numbers, right? That we're encountering as part of the solution of the Schrödinger equation, right? And they will be so important that chemists have devised a letter code for them. Okay, so L equals 0 is called S, 1 is called P, 2 is called D, 3 is called F. And these letters come from spectroscopy. S refers to sharp, P principal, D diffuse. People were studying different spectral lines, so they came up with this letter code. Okay, but what's now cool is that this familiar chemistry notation of electronic states of the hydrogen atom and other atoms, 1s, 2s, etc. Now you can understand them as a compressed notation of wave functions. Okay, so basically here you see this wave function written in explicit detail, showing both the radial part, the angular part. You see that this refers to 1s because the principal quantum number is 1, L is equal to 0, right? So you can, and if you write it in expanded form with these Laguerre polynomials and these spherical harmonics, it's going to look like a mess. Okay, so it's much more concise to refer to it as 1s, and then you can always look up the table. But important concept here is that these notations of 1s, 2s, 2p, 3d, etc., they refer to a single electron wave functions. All right. So all three quantum numbers are going to matter for the wave functions. Energy only depends on n, but wave function c depends on all three of them. In fact, all four of them we'll see once we account for spin quantum number. Okay, so there's going to be, let me write the n first. There's going to be n, L, ml, and in the future there'll also be ms. You can also write it in Dirac notation, nl, ml, ms, right? Or chemistry notation, we can just write it as n and then l. right, and then ml, this kind of notation, 1s, 2p, 2d, etc. All right, thanks to the beautiful symmetry, spherical symmetry of the hydrogen atom, there's going to be a huge energetic degeneracy, and if you count for the spin, it's going to be 2 times n squared. Okay, so every energy level that corresponds to some value of n, let's say n is equal to 1, n is equal to 2, is going to have 2 times 1 degeneracy, 2 times 2 to the power of 2 energetic degeneracy, and this can be all detected in spectroscopy. Okay, so these are the full wave functions now that include both the radial and the spherical part, and you can look at them and you can appreciate that these guys are going to have nodes not only because of the radial part but also because the angular part can contribute to zeros of the wave function, right? So cosine is going to turn 0 at pi half, and the sine is going to turn 0 at pi, and you have the radial functions contributing to 0. So it's going to lead to all kinds of funny shapes for these wave functions, and that's what we're going to study in the next lecture. Okay, and to motivate the next lecture, right, we are going to remember that once we have these wave functions, there's all kinds of interesting computations we can do, and the tool for doing these computations is to calculate these average or expectation expressions. Okay, so if you have some operator A, right, you can sandwich it with your eigenfunctions, or your wave functions. That can, sometimes they can be an eigenfunctions, right, and you can get the average expressions. You can get, the average kinetic energy, average potential energy, average, distance, right? This A could be anything, could be distance squared, could be kinetic energy, potential energy. And since electrons behave probabilistically, we can only speak in terms of averages. Okay, and this is the big conceptual difference from the Bohr model, right, which was a wrong mechanical model of the atom that had this picture of electrons rotating on these deterministic orbits, which is not true, is not something that's consistent with experiments. In reality, electron is found here and there with different probabilities, and the maximum we can maximum information we can extract is in terms of the averages and probabilities to be in different points in space. So here are some interesting quantities. What's the average distance of the electron with respect to the nucleus? You see that it's a function that depends now on n as well as L. Okay, so this is something that you get by calculating, right, by taking the quantum wave function that depends on n, L, and ml, and then sandwich in between two wave functions, Lm, and then do an integral over 3D space, and you end up with these expressions. Okay, and so here already you can see something very interesting. You see that the average distance grows with quantum number n. You can see that n to the power of 4 also depends on quantum number L. So there's going to be some nice interplay, right, between quantum numbers n, L, and the average position, right, of the electron, and this is going to have consequences for electronic shells and bonding in molecules and structure of multi-electron atoms. You can also compute some other quantities that are useful in other spectroscopies and NMR spectroscopies, in dipole-dipole interactions. So these expressions of 1 over r average or 1 over r square is going to feature in different expressions, so we'll reuse them when the time is right. But for now, this expression is going to explain us a whole bunch of phenomena that that accompany H atom and multi-electron atom. And also this expression you can use to solve some problems. You'll be given this expression in your exam sheets. So if you want to calculate the average distance of the electron, that's, let's say, is in a 2p orbital, all you have to do is that grab n equal 2, grab L equal 1, plug into this expression, and you'll have the average distance. All right, guys, so this concludes the first lecture on the hydrogen atom. Coming up is the lecture about atomic orbitals and shapes of the atomic orbitals. Really beautiful lecture. So stay tuned. I'm gonna grab a tea and then start another video.